This presentation, we will focus on the van der Waals equation and non-ideal behaviors of gas. There are three main learning objectives today. The first is to understand what non-ideal behaviors of gases are. The second is to know the van der Waals equation. And the third is to go more in depth and explain the origins of A and B. If you do not understand these concepts during the slides, I will be explaining them on the last slide. So let's begin by talking about non-ideal behaviors of gas. But before we start talking about this, we must take a step back and know what ideal gas behaviors are. So ideal gas behaviors have no attraction between the gas particles, which means they move independently from each other, as you can see in the diagram provided here. In other terms, they have no intermolecular forces between the particles. This is usually represented by ideal gas equation, which is right here. PV equals nRT. So for non-ideal behaviors of gases, they do have an attractive force between the particles. As we discussed before, it's called the intermolecular forces between the particles. As you can see in this diagram with the arrows, they are attracted to a particle. But how do we calculate this, you might be wondering? Well, this is where the van der Waals equation will come into play. The van der Waals equation is an improved version of the ideal gas equation shown in the previous slide that was highlighted in blue. But what type of improvements are made to the ideal gas equation, you might be wondering? Well, before we answer the how, we must know the basic variables in the equation. The basic variables are going to be the pressure, volume, number of moles, constant, and the temperature. As I said before, the van der Waals equation is based off of the ideal gas equation. And you can see these basic variables can be found in the ideal gas equation. Now you might be wondering what A and B represent. Before I tell you this, I'm going to state how great of an equation this is because it shows the non-ideal behaviors of gases because it includes the intermolecular forces and the volume of the actual particles. So A here is going to represent the attractive force between particles. And B is going to represent the size of the gas particles. So A is going to be added to pressure. This is going to make the ideal pressure for the equation. This is then going to be multiplied by the ideal volume. And may I state before we move on that now with B being the size of the actual gas particles, it is not dependent on the volume of the container, such as the ideal gas equation is. How do we get A and B though? A and B are unique to each particle. In the table that is provided, you can also find this in the textbook, it shows that A and B are constants. So you can tell from the chart that A is greater than B, but for the gases, numbers could be greatly different as seen in sulfur dioxide, where A is dramatically different than B. But for hydrogen, it's not such a dramatic difference from A and B. These numbers are usually given to you in an equation or provided in a table such as this. What does the A value mean though? Let's take ammonia for instance. It has a high value of A, which means the intermolecular force between the particles will be strong, and in helium the intermolecular force will be weak. Gases that have small A values such as helium and hydrogen need to be cooled down to almost an absolute zero before they become in their liquid states, as seen in the diagram here. When cold air is introduced, the kinetic energy, which is the rate at which the particles moves slow down, which causes them to become more dense, creating the liquid, as you can see in the diagram provided. Let's try an application question. The question states, calculate the pressure of 1 mole of chlorine in a volume of 5 liters at a temperature of negative 73.15 Celsius. Given that A is 6.49 and B is 0.0569. Pause the video and try this for yourself first. So first, let's find the givens in the question. It gives us the number of moles, the volume, the temperature, and the A and B value. So what is it asking for? Well, it's asking for the pressure. So before we begin this question, we must convert Celsius into kelvins, which is going to be 200 kelvins. And given with the van der Waals equation, we're going to do P plus A multiplied by N divided by B to the exponent 2. And we're going to multiply this whole thing by volume, subtract number of moles, and B, which is going to equal out to number of moles, constant, and temperature. So now we have to plug these numbers in. So now since we plugged these in, we can do some of the calculations. So P plus 0.2596 multiplies by 4.94 equaling 6.4. Now we are going to have to subtract 0.2596 from each side of the equation. This will give us P plus 0.2596 equaling 3.32. So in conclusion, the non-ideal behaviors of gases have intermolecular forces. The van der Waals equation is more accurate than the ideal gas equation. And A is intermolecular attraction, and B is the size of gas particles.